Welcome to another Grandmaster video. This is the first of the series of lessons to teach you everything about differentiation. This video series is mostly suitable for advanced level students. However, there's no limitation. Anyone who wish to learn basics of differentiation are welcome. Don't forget to like, comment, and share this video and to subscribe us. Let us first revise how to calculate the gradient of a straight line graph. You can work out the gradient m of the line joining the point with coordinates x1, y1 to the point with coordinates x2, y2 by using the following formula, which is m gradient equals to y2 minus y1 over x2 minus x1. Be careful, do not change the order of the coordinates. If you change the order of y coordinates, make sure to change the order of x coordinates also. Now, let's learn how to calculate the gradient of a curved graph. The gradient of a curve changes as you move along it. The gradient of a curve at a specific point is defined as being the same as the gradient of the tangent to the curve at that point. You cannot calculate the gradient of the tangent directly, as you know only one point on the tangent, and it requires 2 points to calculate the gradient of a line. Therefore, to find the gradient of the tangent at a point B on a curve, as shown in this diagram, with a known equation, you can find the gradient of chords joining B to the other points close to B on the curve. You can then investigate the values of these gradients as the other points become closer to B. You should find the values become very close to a limiting value, which is the value of the gradient of the tangent and is also the gradient of the curve at the point B. Now, let's try to devise a formula for the gradient of the function fx x to the power 2. In the following sketch, the gradient of the tangent y equals fx at a point B is found by starting with the gradient of a chord BC. Remember that the gradient of the tangent at any particular point is the rate of change of y with respect to x. The point B is the point with coordinates x, x squared according to our function, and the point C is the point near to B with the coordinates x plus h, x plus h squared. Here the square should be outside the bracket. It is shown correctly in the diagram. Now, let's try to find out the gradient of the chord BC. So, gradient of the chord BC should be difference in y coordinates divided by difference in x coordinates. Y coordinate at C is x plus h squared. Y coordinate at B is x squared. So the difference of these two coordinates should give you x plus h squared minus x squared divided by difference in x coordinates. X coordinate at C is x plus h. X coordinate at B is x. So the difference in x coordinate should give you x plus h minus x. Now, we can simplify this expression. When you expand the bracket x plus h squared, you get x squared plus 2hx plus h squared minus x squared over h plus h minus x. Here you should be able to understand that x squared is cancelled out with minus x squared and plus x is cancelled out with minus x. Therefore, we get the expression as 2hx plus h squared over h. We can simplify this further by taking out h term from the numerator. That gives us h times 2x plus h over h. So the final expression simplifies to 2x plus h. Then we will look at this formula. So the gradient of chord BC is 2x plus h. But we want the gradient of the tangent at B. In order to get the gradient of tangent at B, we have to send h value of h to 0. We have to make the value of h to 0. So this is denoted by this. So as h becomes smaller, the gradient of the chord becomes much closer to the gradient of the tangent to the curve at the point B. The gradient of the tangent at point B to the curve with equation y equals x squared is therefore given by the formula 2x, or the gradient is given by 2x. We will look at the notation in this step. The gradient formula for y equals fx is given by the equation gradient f dash x, where f dash x is called the derived function. Remember, this is a notation. Therefore, if you have a function in the form of fx equal to x squared, its f dash x, or the derived function, is equal to 2x. Now, let's look at the general formula for the gradient of a function in the form of fx equal to x to the power n. We will again go back to the previous diagram and the formula. So the gradient of BC chord can be given by f x plus h minus fx over x plus h minus x. In other words, difference in y coordinates between B and C divided by difference in x coordinates. As h value reaches to 0, point C goes to point B. So point C will reach to point B along the curve. So chord BC becomes the tangent at B, and the value of above expression becomes the gradient of tangent at B. Now we can denote this with the following notation. We know that gradient of the tangent at B is called the derived function. So it can be denoted with f dash x. So we can define f dash x as limit h goes to 0, fx plus h minus fx over h. So this part of this notation represents that value of h is sent to 0. Remember, the reason we have to write this limit notation is we cannot divide a certain expression by 0 because it is undefined. However, when we write in this form, it means it does not go to 0, but it goes to a point very close to 0, which is almost 0. So we can avoid that undefined situation. Now, using this definition, we can differentiate any function in the form of fx equal to x to the power n. Let's look at an example. Let's try to find out an expression, derived function f dash x, when fx is equal to x to the power 3. We will again consider the general formula, which is f dash x equals to limit h goes to 0, f x plus h minus fx over x plus h minus x. Now, since fx is x to the power 3, we can substitute this x to the power 3 instead of x, fx and fx plus h. So here, instead of fx, we substitute x to the power 3. And when you substitute x plus h instead of x, we get x plus h to the power 3 over x plus h minus x. Now, we can expand this binomial expression using binomial expansion. You should be familiar with binomial expansion. So it gives us x plus 3, x to the power 3 plus 3x squared h plus 3x h squared plus h to the power 3 minus h cubed over x plus h minus x when limit goes to 0. We can simplify this expression. So x to the power 3 and minus x to the power 3 cancels out, and plus x and minus x cancels out, which simplifies the expression to the following step. Now, we can also take out h term from the numerator and cancel out with the h term at the denominator. That simplifies our expression to limit h goes to 0, 3x squared plus 3xh plus h squared. Now, as h goes to 0, the limiting value becomes 3x squared, since 3xh and h squared terms also goes to 0. So when fx is x to the power 3, f dash x, or our derived function, is 3x squared. We'll look at another example. Let's try to obtain f dash x when fx is 1 over x. Again, we have to use the general formula, which is limit h goes to 0, fx plus h minus fx over x plus h minus x. Now, when we substitute 1 over x instead of x in the function, so we get 1 over x here in fx, and when you substitute x plus h in the function, we get 1 over x plus h divided by x plus h minus x. We can simplify this expression by taking the common denominator in the upper part. That gives us x minus x plus h over x times x plus h, and the in the denominator we get the expression x plus h minus x. We can simplify this further. Here plus x and minus x cancel out, so you get h minus h, and then again we can take the common denominator, which gives us minus h over x times x plus h divided by h. So our expression then simplifies to minus 1 over x squared plus xh when limit goes to 0. So as h goes to 0 in this expression, the limiting value becomes minus 1 over x squared, which can also be written as minus x to the power minus 2. So when fx equal to x to the power minus 1, or in other words 1 over x, f dash x, or our derived function, become minus 1 times x to the power minus 2. Now let's look at the derivative of the function of fx in the form of x to the power n. So fx when fx equal to x to the power 2, it gives us f dash x as 2x to the power 2 minus 1. In other words, 2x to the power 1. When fx equal to x to the power 3, our f dash x equals to 3x to the power 3 minus 1, which is 3x to the power 2. This one I can write as 2x to the power 1, and this one I can write it as 3x to the power 2. And similarly, when fx is 1 over x or x to the power minus 1, it gives us f dash x as minus 1 times x to the power minus 1 minus 1, which simplifies minus 1 x to the power minus 2. Also, if you remember, if you have a function of fx which is equal to x, or in other words, x to the power 1, it gives f dash x as 1 x to the power 1 minus 1. In other words, 1 times x to the power 0. In other words, we know that x to the power 0 is 1, therefore our gradient is 1, which is actually fx equal to x is the function of y equals x. If you sketch a graph of this, you get a straight line passing through the origin with a gradient of 1. So we know that obviously gradient of this f dash x of this function should be equals to 1. Similarly, if you think of fx function, which is x equal to 0, x to the power fx equal to x to the power 0, it gives us f dash x as 0 times x to the power 0 minus 1, which is eventually leads to 0. So we know that x to the power 0 is equal to 1, which is a constant. So if the function is constant, something like this, where we know that if the function or the graph is parallel to the x-axis, then its gradient should be equal to 0. That's why we get f dash x 0 in this situation. Therefore, we can write a general function or a general formula rule to determine the f dash x or the derived function for a function in the form of x to the power n. So in general, it can be shown that if fx equal to x to the power n, where n is a real number, then f dash x can be given as n times x to the power n minus 1. In words, so the original power, remember, the original power multiplies the expression, and then the power of x is reduced by 1. This step is very important to remember. So that's how we obtain the derivative function of a function of x to the power n. Let's look at some examples. So find the derived functions when fx equal to one of these expressions. We will again keep our general formula aside, so it's much easier to apply this rule. So first one is x to the power 6. We have to apply this f dash x equal to nx to the power n minus 1, which gives us x to the power 6 can be written as 6 times x to the power 6 minus 1, which simplifies to 6 times x to the power 5. Similarly, if you apply this rule to x to the power half, we bring half down, and then x to the power half minus 1, which gives us half times x to the power minus half. So this can be simplified, if you want, in the form of 1 over 2 x to the power half, bringing the x down, or by converting the index to a positive value, we get 2x to the power half. This can also be written in the form of 1 over 2 root x, since a fraction power of any number is as root. So this should be the final answer. Similarly, we can obtain the derived function for x to the power minus 2. So bring minus 2 down and multiply with x to the power minus 2 minus 1, which gives us minus 2 times x to the power minus 3. If you want to write this as a positive index, we can bring this x to the power 3 downward to the denominator. So we get minus 2 over x to the power 3. Then we look at part D. Before you are going to get an derived function for this function, it would be much convenient if we simplify this expression, since both the terms are in x base. So using the index rules or indices, we can simplify this to x to the power 1 minus 5. That gives us x to the power minus 4. So still I'm not finding the derived function. Still I'm simplifying the fx function, which is, this is still fx, and then I can obtain f dash x, which gives me minus 4 times x to the power minus 4 minus 1, which simplifies to minus 4 x to the power minus 5. Then we can write the index as a positive value, so you get minus 4 over x to the power 5, which is f dash x. Similarly, the final part can be derived, but before that we have to simplify the original fx function to get a single term. So using index rules, we get x to the power 2 plus 3, which is x to the power 5, and our f dash x function can be therefore written as 5 x to the power 4. We'll move on to another set of problems. Here you have several questions, several sums which you can try out. I will give you the answers in the next slide. Again, we will take our general formula. I'm not going to discuss all of these sums, but I will discuss few sums which I think might be worth discussing. You can find the derived function for x to the power 7, x to the power 8, x to the power 4. But I will explain how to obtain the derived function of x to the power 3. So f dash x is, we can using this formula, nx to the power n minus 1. So we bring 1 over 3 down, and that gives us x to the power 1 over 3 minus 1. Then we can simplify this 1 over 3. X to the power 1 over 3 minus 1 gives us, let's simplify it on a side, 1 over 3 minus 1. So we can take the common denominator as 3 here. So that gives us 3 also here. So we get 1 minus 3, that is minus 2 over 3. So the power should be minus 2 over 3. If we want, we can write it, this power, as a positive value. So you get 1 over 3 to the 3 times x to the power 2 over 3. So question 5 is similar to our question 4. And then question 7 and 8 I have explained in the previous examples. For question 6, we can write this root as a power of x. First we simplify this expression, so we get x to the power 1 over 3. So this is cubic root. So cubic root can be written as x to the power 1 over 3. So that would become same as the fourth problem. Now you should be able to simplify this. Similarly, question 9, 1 over x to the power 2. It's much convenient if you first simplify it to the form x to the power n, which is x to the power minus 2. Now we can find out its derivative f dash x as minus 2 times x to the power minus 2 minus 1 gives us minus 2x to the power minus 3. If you want, you can write this in with a positive index. So 10th problem is similar, 11th problem, and then 13, 14, and all the way up to these 18 problems. They are very similar to the last two problems that we discussed in the examples. With that, we will finish the first part of differentiation lesson. See you with another interesting video for the differentiation part 2. Stay tuned to our channel. Make sure to subscribe us and also like and share our video.